Yeah, thanks, Bob. Yes. So this is going to be about a lab perspective on all of this. So I'm going to be considering cylinders, and in some cases, pretty tall cylinders. So when I talk about rotating Rayleigh-Bénard convection, I'm going to be referring to the system sketched on the left there. So very simple body of fluid confined within a cylinder, heated from below, cooled from above, rotating about a vertical axis. In some cases, I'm going to be comparing to this infinite layer, if you wish, or perhaps the periodic domain that we can apply in numerical simulations sometime. And thanks to John for the rigorous introduction. So I guess some parts can go a bit quicker than intended, but okay, I can see that I can connect to a lot of what John has told us just before the break. So rotating Rayleigh-Bénard convection, I'm going to be using the language Rayleigh, Prandtl, and Ekman for the thermal forcing, the fluid properties, and the strength of viscous forces compared to the Coriolis forces. Now, the response parameters also already pop by. So if we set the previous three input parameters, we are looking for the output. And one of the main output parameters is the Nusselt number, efficiency of the convective heat transfer. You can also write total heat transfer normalized by the conductive contribution, where total heat transfer is convection and conduction. So Nusselt number equals 1 means that there's no fluid motion going on. We can actually measure this parameter quite well in experiments. Another thing that will come out is the Reynolds number, so the magnitude of the velocity fluctuations that happen. And another way to write this is inertia over viscosity, and we can compute it as such. I will not have time to go too much into the Reynolds number. I'll be focusing more on Nusselt number for this talk. But the ultimate goal for me as an experimental fluid dynamicist is to try to know the Nusselt number and the Reynolds number as a function of these three input parameters. And we might think about including gamma, the aspect ratio there too. Now, we've seen plenty of these sketches already. And for me, just the important thing to note is that we are looking at very high Rayleigh numbers and very small Ekman numbers. And we are going to try our best to get as close as possible to these numbers in a lab experiment. And as also already shown, this cylinder that I'm going to be working with is to be located somewhere on a polar region of this convective zone. And of course, we hope that the side walls won't matter too much. Well, they're probably going to. So, quick contents of this presentation. So I'm first going to give a brief history of the lab investigations into turbulent rotating convection, and in particular with regard to sidewall effects. And then some ideas on how to push towards geophysically and astrophysically relevant parameter settings. And then about these wall modes, how can you detect them in the lab, and possibly how can you get rid of them? So let's start off with the first one. So the history basically starts with a theoretical investigation by Chandrasekhar, who did the linear stability analysis. And he found that rotation actually stabilizes convection, right? This has also been alluded to by John already. If you add rotation, you move to the right in this graph, and you need to achieve a higher Rayleigh number to apply a larger temperature difference before convection even sets in. And from this analysis, there are these asymptotic relations that John already introduced. So critical Rayleigh number goes up, and the critical length scale of convective onset will actually shrink. And these were the theoretical predictions. Quite soon thereafter, 2 years later roughly, there was already an experimental verification by Nakagawa and Frenzen in a thin water layer. And the diagnostic that they used was actually to measure temperatures in the bulk of the liquid. And they could then see by the response of these temperature probes whether convection had set in. And this gives this very nice diagram with here, once again, the Taylor number, which is actually the inverse square of the Ekman number. So rotation increases to the right. And the critical Rayleigh number before convection sets in clearly nicely matches the prediction from Chandrasekhar, the line. Now, emphasis that they used basically bulk measurements to check for onset of convection. Now, the next big investigation was by Rossby. And I really like this very detailed sketch of the convection experiment. We don't do this nowadays anymore. It's quite a pity. But this is a device that he used. And the convection cell is actually right here. There is this thin layer. He could also change the height around a bit. And this is what he would be using for investigations into turbulent rotating convection, because this is the first extensive exploration of heat transfer in the turbulent regime that I could find. And he did quite a bit. He actually used 3 different working fluids. So mercury, water, and silicone oil. That one is between brackets because this is mostly for visualization. And for water, he could get to quite nice parameter values already. The Rayleigh number clear into the turbulent regime and the Ekman number, which is already quite small. So he did a lot of heat transfer data. And this is the main result from the paper, showing in this diagram as a function of the Taylor number once again, so rotation increasing from left to right. And now as a function of the Rayleigh number, vertically, the Nusselt number by these contours. Now the prediction from Chandrasekhar for onset of convection is shown here with this dashed dotted line, meaning that anything below should be purely conductive. Nusselt should be exactly equal to 1. And these are contours of Nusselt that go up and up that show that indeed convection starts. And then there's this particular result. There's a bit of convection below the critical line, below Chandrasekhar's prediction. And there's this nice piece of the paper. We do not understand why this should be. It is found to be quite reproducible. Well, that's good. So there's something to be had there. But this tiny little triangle, it was unknown at the time. And in fact, he did not really do visualization in this particular regime. He could not really validate what was going on. So open question. Then a bit later, another experiment using liquid helium. So quite different working fluid. But also there, the onset below the critical Rayleigh number was confirmed. So this is now the Rayleigh number and the Nusselt number at some constant rotation rate. And you can see here, right below the critical point, which would be here, there is already a bit of convection to be found. And by then, they also had the possibility to change the aspect ratio, and they could clearly show that the onset of convection is actually a function of the aspect ratio of the cylinder, where once again the thick line is the prediction from Chandrasekhar. And as you can see, as the aspect ratio goes down, the critical Rayleigh number actually also seems to go down in this representation. Now, by then, there was already some additional theory being done. So there's an investigation on the onset of convection in cylindrical domains in particular. And this paper by Buell and Ketten have introduced this most unstable mode, which already looks quite a bit like our wall modes. It's only that they proposed that these are static modes, that they are not going to change as a function of time. So this is, but the overall principles and ideas seem to match with these measurements. So that is the next step, let's say. But then it's time to really validate this, and now it's time for some visualizations. And these came a few years later. investigations done by Zhong et al., where also Bob was involved. And these shadow graph visualizations clearly show the presence of this wall mode with these bright and dark spots being the up and down going lobes of the wall mode. And these also showed that these things are actually precessing most of the time against the direction of rotation. And by then, there has been some theoretical developments also that there is these wall modes, the modes that are precessing, that were found also theoretically, and this gave a very nice quantitative match. There's a question? Yes?
How do you do shadow graph in that geometry, like going downwards?
It's the cell was transparent on both sides, I believe, right?
No, you do. You have a mirror on the bottom, and you pass the light through, and then you come back up. So the quality of the shadow graph wasn't very good because the shadow graph was in the fixed frame, and the thing was rotating. We fixed that later on, but we got it.
It's nice to have the people in the audience.
Can I ask another question?
Yes.
This paper by Rossby, which you cited, is it father Rossby or son Rossby?
I'm sorry?
Which Rossby was it, father or son?
It's the son thing.
It's it's not the Rossby, the son, I believe, I don't know whether they are actually related by family.
Yeah, they are. They
are.
are.
Okay.
Yeah, and he was actually National Academy of Engineering. He built devices. Actually, he sent me all his data, so anyone who wants that data from that 69 paper, it's very fun to tie to it.
He also wound up in the hospital for mercury poisoning. Real experimentalist.
Okay, so, but then a bit farther from onset, the same study would show the development. You can see the nice vertical structures that appear. And looking at the sidewall, well, nothing much is happening. So probably the turbulence will wash away these wall modes. End of story. That's it. Let's go. So this is the status of the 1990s. And now it's time to start pushing the envelope, because now let's try to get closer to these geophysically, astrophysically relevant parameter values. And this is the next part. So a quick phase diagram of rotating convection. I will going to show some results as a function of Rayleigh and Ekman. Now rotation actually increases to the left because now we're using Ekman. And this slide I've been using many times before, but waking up very early this morning from jet lag, I actually realized that I forgot to put in the line of onset of wall mode convection, which might be important for this meeting. So this is just indicative, by the way. The numbers are not really one-to-one matching, but to give an idea. So if we move at a certain Ekman number upwards, we would first encounter onset of wall mode convection. But as we saw before, it doesn't really contribute that much to the convective heat transfer. And then pretty soon, we will reach the Chandrasekhar limit, and then bulk convection will set in. Now, if we move upward all the way, increase the Rayleigh number very much, then eventually we will have so much thermal driving that rotation basically becomes unimportant again. So let's call this non-rotating convection. Then there's a range in between where you will see some effects on the flow field, but nothing too drastic. And this, you could say, is rotation-affected flow, perhaps. But then in between, there is this slice of the pie that becomes bigger and bigger as we move to the left. And this is this so-called geostrophic regime, already mentioned. And if we extrapolate everything, then we believe that most of these big geophysical and astrophysical systems fall into this regime. So this is the one that we need to explore, and this is the one that we want to understand to make reasonable outward extrapolations. So the task is, given these constraints, let's build a device and let's push the envelope. So how are we going to do this? Well, we need to make Rayleigh as large as we can while simultaneously making Ekman as small as possible. Looking at the definitions, well, the obvious candidate is the height. So making a tall setup gives you high Rayleigh numbers and small Ekman numbers. But at the same time, there are also some practical constraints that we can also take into account. And the first one of those is there will be a minimal temperature difference that we can reasonably measure up to a certain accuracy in a laboratory device, or there is a minimal heat flux that we can realistically apply. Both of these will lead to some kind of lower limit for the temperature difference, lower limit on Rayleigh for any given geometry. Now, of course, on the opposite side, there will also be a maximal delta T that we can reasonably apply. For example, with water, of course, delta T will never come really close to 100 degrees for obvious reasons. At the same time, it's also difficult to add really large amounts of heat to such a system, possibly in practice. Another topic that was not yet mentioned, but is nice to try and keep track of, is to try and retain Boussinesq conditions, meaning that the temperature differences are small enough to say that at least for this range, we can consider the fluid properties to be constant independent of temperature. In an experiment, easily to violate this requirement, but if you want to be able to compare to theory and numerical simulations where this is often retained, it's good to keep this in mind, at least. So we will have an upper limit on the Rayleigh number. And then about rotation, well, you might think, okay, Ekman number, make it as small as possible, let's spin this thing as fast as we can. But then centrifugal buoyancy will kick in. So here's the fruit number. So what is typically done is to take the rotation rate squared and the radius of the cylinder and compare the value. This is the maximal value of centrifugal acceleration in this cylindrical domain. Compare it to gravity, and this should be small. Less than 10% or something like that. That's the rule of thumb that is typically applied. So, of course, we should make sure that we're still looking at vertical buoyancy rather than radially outward buoyancy. So this is a lower limit on the Ekman number that we can achieve. And there's also an upper limit on the Ekman number that we can realize in any geometry. And this is related with the length scale, the horizontal length scale of convection that we expect. So the critical wavelength for onset of convection has already been passed by several times. And Keith Julian in the simulations has shown that this remains an important length scale throughout, also deep into the turbulent regime. So what we should do is make sure that our cylinder is wide enough to capture at least several of these length scales. And in this case, I chose 10 as a realistic lower limit. And then the argument went, okay, then we're probably safe from any sidewall influences. And this gives an upper limit on the Ekman number. And if you run the numbers, you can find that the solution is to build tall, slender setups. So this is an overview that comes from this paper in 2018, where the first author is also in the audience. And indeed, several labs around the world actually came to similar conclusions, where it is profitable to build tall, slender setups. And this goes for many different working fluids. So there's liquid gallium, there's cryogenic helium, then there's 2 water setups. And there's also one setup from Göttingen where there's a big pressure vessel where they could use pressurized gases. In particular, this sulfur hexafluoride gas, which is particularly suited to get to very high Rayleigh numbers. And as you can see, yeah, size is increasing ever and ever so much. up to 4 meters in the case of this device that is indeed in Eindhoven. Yeah. So these devices were put into practice. The measurements started, and then some funny things started to happen. First, I want to share the data from the Göttingen U-boat. This setup, they had put thermistors on the sidewall or slightly into the working fluid, into this gas. This is a popular measurement technique that actually comes from the non-rotating convection investigations, where the dominant mode is typically one large roll of convection that you can nicely find and quantify by using these temperature probes along the sidewall, because the upgoing side will be hotter than the downgoing side, and therefore the dynamics of this large-scale roll can be nicely monitored with these probes. And I know the principal scientist, or the guy who did all the measurements from this setup personally, and for quite some time he was struggling with the data. So what if you plot a PDF of one of these temperature signals? Without rotation, you would actually see a sort of Gaussian distribution, even though we have this large-scale circulation, so that turns out to average out quite well. But then, after adding rotation, there's this funny bimodal distribution, and they couldn't really figure out what it was. And poor Dennis van Geel spent quite a bit of time thinking about it, and this never got really resolved up to around 2020. At the same time, we were building this big machine in Eindhoven, which is actually a modular design, so you can also use different heights by different segments to be included. Also took care of the insulation for the heat transfer measurements, where there's actually different individual sections, each with their own heater, and they would be set to have a temperature equal to the temperature measured at that particular height. So we would also have temperature probes in the sidewall. And this helps you to actually also reduce the conductive losses to the outside, so that you're really measuring the heat flux that is heat put in from the bottom and goes out at the top. Now, the first results came in for the Nusselt number. This is at a constant Ekman number 10 minus 7, Nusselt as a function of Rayleigh, and I've included a few studies here. So these were the data from Jonathan Cheng in John Arnoux's lab for the water setup that was there here at UCLA. The measurements in Eindhoven nicely agreed with that, so that's good. At least the experiments in the cylinders were agreeing. But then compared to these periodic layer simulations, we see that there's a significant gap, something like a factor 2 at least. So what's going on there? Somehow there's a lot more convective heat transfer in a rotating cylinder than in this periodic domain. And then around that time, independently, the people in Göttingen and we in Eindhoven decided to do some numerical simulations at these kinds of parameter values. And I'm going to show you some movies that show the vertical velocity at mid-height in this system. Left for a reasonably low Rayleigh number, right for a reasonably high Rayleigh number. These values are actually identical to what we could apply in the experiment. And well, the left one in particular is pretty obvious. Wall modes are back with a vengeance in some way. Even in this highly turbulent situation, you can still recognize the 1/2 red, 1/2 blue type of structure. And there's also a dramatic effect, in particular on this one, where blue and red meet. you have these jet-like intrusions, and they actually kind of dominate the entire bulk too. So that is what we found. We also found, given the strong vertical velocities at the sidewall, this thing is also contributing a lot to the overall convective heat transfer. So the wall modes persist. And this is, of course, what is also found in Göttingen. Yeah, another.
Sorry, on the previous slide, you've drawn these suggestive kind of purple circles. Was that just done by eye, or is there something? Is there a prediction for that?
So this is the radius or the size of the boundary there according to our own criterion that is based on profiles of RMS vertical velocity. There's RMS vertical velocity is kind of constant for most of the domain, but then shows up a peak, and then where the peak and the constant value meet. That was our criterion, and yeah, it's just an arbitrary criterion for the thickness.
And from the theory of wall modes, is it expected for it to get larger at higher Rayleigh number?
No, the wall modes just say there's one particular horizontal scale that scales as Ekman to the power 1/3, of course. But in fact, the wall modes just give a complex power of E that shows the profile. And the peak of RMS velocity nicely matches with those predictions. Also for different Ekman numbers, let's say. So they do scale nicely. But this is probably a lot related to the interaction between the wall mode and the turbulent bulk. So this is by no means any linear theory of wall modes anymore. Yeah. There was another remark in the back, yes.
If you had a cylindrical annulus, would you still get the wall modes, or do they need the full cylinder?
Turns out it doesn't really matter which geometry that you apply. If there's a wall, there will be a wall mode. And we might hear a lot more about this, but there's been one investigation where also Edgar Knobloch was involved. And they actually made a sort of Pac-Man shape, so kind of wall pointing into the domain. And this wall mode would nicely go around. Didn't care about the geometry. So these are quite persistent features. Yeah.
What is gamma there? The aspect ratio?
Aspect ratio. This is 1/5. So it's 5 times as tall as it is wide. Yeah. Experimental parameters. Yeah.
Just following Daniel's question. So in the case on the left where it looks near, let's say quasi-linear, it is that purple line. If you overplotted the Ekman to the 1/3 Stewartson estimate for UZ, is that where it is? I mean, like, are you already close to it in that case where there's not an incredibly strong interaction with the bulk turbulence?
Yeah, these profiles would nicely match with the Stewartson layer analysis, yes. Yeah. Yeah.
And this is above the onset for convection?
Yes, yes. Yeah, it's above onset for bulk convection, yes. Yeah, definitely, yeah. So this, comparing to the periodic layers, this would like be columnar type convection, while this would be plumes and beyond. So there's definitely a transition between the two, which was also quite interesting to investigate. In the papers, we discuss a bit more about this. Yeah. So wall modes persist. Also in the Göttingen simulations, we have already seen images like this, where they plot as a function of the azimuthal angle and time, in this case the temperature, showing that there's a warm half and a cold half, and the thing is nicely rotating against the direction of rotation. And here, this is actually directly averaging the convective heat flux, which you can also conveniently do in numerical simulations, showing that definitely the sidewall region is contributing a lot. And this is the factor 2 that we saw in the global measurements before. And here for our simulations, quite a lot the same. This is vertical velocity, where we also see similar features. This was all quite well in agreement. Similar conclusion, the wall modes persist and might even become more prominent at these parameter values. So we also did some more tricks. Since this is such a nice division into two halves, and this thing is precessing, for each time step we could also use the azimuthal profile to define a certain orientation, and then to rotate every single snapshot back to a common phase, and then do the averaging to really see how this flow field will look like. And this is what we've summarized here. So this is a bit much perhaps to digest, but this is 3 different horizontal cross sections at different heights, 3/4, 1/2, and 1/4 of the height, showing vertical velocity, radial velocity, and azimuthal velocity. So vertical velocity, as we saw, there's the blue half and the red half, which is common across all heights. The radial velocity shows these prominent negative patches. These are the radially inward pointing jet-like intrusions. And then the azimuthal velocity also shows a distinct structure, that there's a sort of 2 layers type of structure with cyclonic and anticyclonic bands existing quite close together. So there's a lot of dynamics within this wall mode at the same time. So we see, actually, if you look at the bulk, there's basically no dependence on height. So this is all pretty geostrophic in that regard, that there's not much happening as a function of z. And the 2 jets are the most prominent features here. And this nicely matches also with the dynamical picture that you can get from the movie. Now, at slightly larger Rayleigh number, this other type, then we can see some slight differences. The overall picture looks quite similar, but there are some different nuances here. So the radial velocity in particular now has distinct differences, where there are still these inward-like regions, but now where they meet, things should be going radially outward again. And this really sets up a sort of 4-vortex state in that regard. We can now see that the wall mode, or the sidewall region, has become a bit thicker, probably because of these interactions between bulk and boundary layer. The azimuthal velocity, now the distinct 2-band structure has also vanished a bit further, but overall, similar picture. And still, the bulk is quite nicely geostrophic as it was before. Yes?
It seems like at the 1/4 and 3/4, the azimuthal velocity has switched signs.
Yes.
Is there a reason for that? I mean, there's a reason for it, but do you have an explanation, or what's happening there?
Yeah, this is something that we haven't really figured out completely yet. It's not coming from the theory of wall modes per se. So this is probably some nonlinear effect that happens because of being at higher Rayleigh numbers. So there's definitely some stuff that is interesting here, perhaps. Somebody, you might have not noticed it, but there's also this funny little mirrored VR peak that is on opposite sides. Well, there's no real reason to have something like that. That's all open, I would say.
When the azimuthal flow switches direction, does the wave precession also switch direction?
No. No, the waves really keep on going. Yeah.
Okay, thank you.
Yeah. Yeah.
Do inertial waves play any role in this experiment?
Possibly. I'm not sure. Never really looked deep into it, but we did see effects of inertial waves in a smaller scale rotating convection setups, where we did particle tracking. And at some moment, when we were at a low critical Rayleigh number, the particles would start to go in a sinusoidal path. And would be not surprised if in this regime, inertial waves would be present.
If you computed the spectra, you would see the effect. Do you have any spectral computer there?
No, not for these, but we'll have a look into it. Yes. Yes, in the back. Yeah.
So why do these modes precess in the first place? And presumably they have a preferred direction.
Yeah. Yeah. Well, what I can say is it comes from the theory. There's no real. Yeah. Yeah. There's a lot that can be said there. So it will get even funnier a bit later on when the mean velocity comes into play. So bear with me, I would say. Yeah. So indeed, you can also have a look by doing averaging over time or averaging over the azimuthal angle, which boils down to the same concept if you average for long enough, because this thing is precessing, so it doesn't really matter. And these are images from the Göttingen simulations, where you can see that very close to the sidewall there is this cyclonic band. So azimuthal velocity going in the same direction as rotation, but in general the bulk actually shows the opposite direction of flow. So these are actually going in opposite directions once again. And this can also be, let's say, summarized in plots like this, where the average azimuthal velocity is plotted as a function of radius, where you can see the bulk is overall going against the direction of rotation, and there's this cyclonic part close to the sidewall. So this is another way to detect these, and this is what the Göttingen group called the boundary zonal flow. So there's definitely some flow also related with this precession of the wall mode. So wall modes are there to stay for now. And how can we detect them in the lab, and how might we be able to get rid of them? And well, the first thing we saw already, these temperature probes. You could say there is a hot part and a cold part to the wall mode if I measure temperature in a circumference. So this I can use to find the orientation of the wall mode from a temperature measurement. There was a question. Yes.
Yeah, sorry if it's a naive question. Can you just explain to us how is it determined that they are not geophysically relevant at all? Like, why do you want to get rid of them in the first place? If you say to us that anytime there's a wall mode, why isn't it?
So if you think about the planetary geometry and our cylinder being up there somewhere, you would hope that the sidewalls are not that important, that you are actually studying a bulk type behavior. Also on the planetary scale, there are boundaries where these things might happen. But for now, yeah, our purpose here was actually to try and study the dynamics that are basically for this bulk type behavior without the sidewall actually dominating the dynamics to some extent. So you might not always want to get rid of them, but you might want to be able to switch them off in a way. That would be nice.
It's separate.
Yeah.
If you're in the tangents.
Yes.
Can you bring on Daphne's question? Should there be wall modes and on tangent cylinders?
Yeah.
Well, possibly.
I was hoping you could tell.
This is why we are here this week, I believe. So.
Have they been seen in spheres, or does it have to be a cylinder?
I think signs have been seen in spheres, but I hope that other people in the audience will show us about this this week. Yes.
Is that possible that they determine the forcing, the nature of the forcing? You are doing convection?
Yes.
You use any other type of forcing, like mechanical forcing, or that the wall mode will be the same or different?
So far, it looks like the wall mode is purely convective indeed in nature. So if you use anything else, they will not appear. In fact, this is going to be an interesting question. The experiment by Basile, I don't know how it is there. Do we have wall modes there?
made in the middle, so we don't quite see the.
Okay.
We have movies in the turbulent state. We don't see much happening in that wall plate here.
Yeah. Yeah.
So if you test your device with some mechanical forcing, you might have rotating turbulence without the wall.
True. Yes, indeed. But then I wouldn't be studying rotating convection.
You will still have a very large, low Ekman number, right?
Yeah, definitely. Sure, there's yeah, indeed, there is some merit there. No, certainly. Yeah. Okay, so dynamics or diagnostics of the wall mode. These temperature probes you can use to mimic these images that we saw before. And as I said, in our device we also have temperature probes on the side. Well, we did not have as many on the circumference. We only had 2 on opposite sides of the cylinder, but at several different heights. But in fact, turns out that you can still recognize the wall mode signature from these measurements. And as an example, I plotted a temperature signal from the thermistor at the top left, and it looks something like this. It's a bit erratic, but there's still some kind of periodicity to it. So we have periods of time where it's slightly warmer and periods of time where it's slightly colder. Just to put things in perspective, this is about 5 hours. So it's a pretty long time scales that we are dealing with here for an experiment. So let's have a look at the opposite probe. And if you look closely, you will see that generally they are in antiphase, as they should be. So that's good. So this is something that we can use. If you then plot the next height, you will see that the darker color is actually nicely in phase with the darker color on the other height. So different sides are in phase. The opposite side nicely matches with the lighter color in antiphase with the darker color there. So this is a nice diagnostic. It goes for all the measured heights that we have. And of course, we could also have a look at the spectra of this signal to get to the precession rate. And this is what we got from our DNS. And it is very nice in agreement with the peak of this power spectrum from the temperature probes. And it's certainly not related with the rotation frequency, which is a much higher frequency overall. So these temperature probes are pretty indirect. We could also measure the flow directly, because that's also an option in the Eindhoven setup. Therefore, we have built this prism-like cylinder part. You can see an actual photograph here. The prism is also filled with water in order to avoid too much refraction on the cylindrical body, because when it's filled with water, it acts as a positive cylindrical lens, and you will not see that much. So there's 2 nice straight faces where we can position cameras, 2 in this case, so that we can apply stereoscopic particle image velocimetry, meaning we have seeding particles in the cylinder, a horizontal light sheet crosses at some height, and by having these 2 viewing angles, we can actually resolve all 3 components of velocity in this plane. Now, some movies, once again for a small Rayleigh number and a high Rayleigh number. And much of the results from the simulations actually reappear again. We have the vertical velocity color-coded and the arrows for horizontal components. There's this nice red half and blue half with the jets going in at the points where they meet. And also in the turbulent case, the more turbulent case, let's see if I can replay it. If you look closely, most of the time you can also see there that there's a partitioning red and blue at the sidewall with inward jets where they meet. And going back to this mean flow structure, if you look closely and squint a bit with your eyes, you can see that there's this 4 vortex type orientation that actually is rotating against the direction of rotation. And so you can see that the sidewall in this case actually sets the entire large-scale bulk dynamics to some extent. So the application of PIV has also been performed in Göttingen. This is in a different setup than the big U-boat experiment. So this is now a tabletop size convection device filled with water, with dimensions of about 20 centimeters height and wide. And they did regular PIV in this system, meaning that you can get the in-plane components of velocity, and thereby getting to this azimuthal and time average profile of the azimuthal velocity component, where once again, close to the wall, there is this cyclonic motion and the bulk being anticyclonic. So the global features that were also found in the DNS were very nicely reproduced in this particular configuration. Okay, and now it's time to move on. Provided that we want to get rid of them, how can we try to get rid of the wall modes? So one idea is to go to a wider cylinder. Well, at these parameter values, we could not easily do this in an experiment, but we did some numerical simulations. So what if we move to an aspect ratio of 0.72 to make it wider? Of course, in a simulation, we don't have any trouble with centrifugation because we can just switch it off, no worries. And we chose this particular aspect ratio because in this aspect ratio, we expect a wall mode with 2 wave numbers in the circumference rather than only 1. And a result from that simulation, you can see wall modes survive, wall modes thrive. Now we have 2 red sections and 2 blue sections, and still where they meet, there is this inward stuff happening. And now the idea was, well, maybe the effect of these jets can only go radially inward up to a certain extent. What if deep inside, perhaps there's unaffected turbulence? There was a question, yes.
Quick one. You said no centrifugation, so in the simulations, your equations are simulating, you turned off the centrifugal force but kept Coriolis?
Yeah, you only need to switch off centrifugal buoyancy, actually, because centrifugal force in general is typically absorbed in the pressure gradient term, yeah. So you don't need to take into account anyway. Yeah. So what we did use some PDFs of the radial velocity component to check for any asymmetries due to these inward jets, and we also used once again this orientation orientation compensating averaging to check the global flow structure here, and this is what comes out. It's the color coding is not that easy to display here, but the overall situation is that now we are actually ending up with 8 of these large-scale type vortices that are actually slaved to the wall mode. So this entire structure will rotate in anticyclonic direction. But there is a certain region in the bulk where we might want to say, perhaps this is unaffected by the wall mode. It's not that practical for experiments, but can be done in principle. So now the other way that has been proposed to get rid of them is by introducing these horizontal fins. And since John had already talked about this before, I can quickly go through. So this is a channel-like convection geometry. This one is periodic in both directions. This one has vertical walls on the 2 long sides and are still periodic in that direction. And here again, irrespective of geometry, these wall modes will appear. And if you would have this as a movie, you would see that these things would be moving along the wall because there is a wall where they can move. That's kind of how it goes. This one, there are walls on these sides, but there are also a certain number of these barriers along the side wall. And by the look of it, kind of similar. They actually also showed that you can get the Nusselt number to correspond very nicely, but then you need to add, in this particular setting of the parameters, 3 wall modes, I believe, and then it would nicely, the Nusselt number would nicely converge to the periodic case. So we've also been trying this idea in a small-scale setup. These are very preliminary results. I need to emphasize this. So we have this nice convection setup where we can actually include 1 to 4 of these rings at heights that we can choose, and we are going to do PIV. At first, PIV looking from the top in a cross-section that is horizontal, and this is a first result. So this is the horizontal velocity component color-coded by vertical vorticity. So this is nothing yet to do with the vertical velocity altogether. Nothing much to conclude from this movie alone, except that there's nothing really obviously happening on the side wall. So this is with one of these fins present. The animation doesn't really show too much, but if we look at some other things, for example, this azimuthal velocity, averaged over time and over the azimuthal angle, we have 0 rips, showing the wall mode, anticyclonic bulk with a cyclonic region close to the side wall. And then you can see that, if anything, perhaps the presence of rips only enhances the mean flow pattern. I don't know yet if this is good or bad. What is interesting to note here, by the way, is that you can see that 0 and 2 rips are kind of similar, and 1 and 3 rips are also kind of similar. And this is probably because we are measuring at the center of the cell, which is just above one of the rips in the 1 and 3 rip cases, and quite far in the 2 rip case. So there's probably also some local influence. So you should be very, very careful with interpreting in all of this. And there's also a region close to the side wall where now it is a bit harder to do PIV because the fins are actually blocking the field of view from above. Now, vertical velocity fluctuations expressed here as the Reynolds number. This one is a bit more puzzling still, where we have the red curve without any barriers, without any fins, showing the profile that we are used to from the other experiments. And then the presence of 2 or 3 fins suddenly leads to this big peak. So if anything, the barriers will also induce significant vertical flow somehow. And this is pretty preliminary. We are now actually conducting some new experiments where the PIV plane is actually vertically, so that we can have a look from a different perspective to see if we can get some more input there, and to see if this is a promising technique to get rid of the wall modes if we want to get rid of them. So let's conclude then. Wall modes are unexpected, persistent part of confined rotation. There's strong contribution to the convective heat transfer, jet-like intrusions that shape the entire interior flow. And how can we deal with them or get rid of them, perhaps? Well, not quite clear. Perhaps we can make the domain wider so that the walls are simply farther away. We might have an interior region that's unaffected, or to use these horizontal fins to block them, but that might then again cause additional secondary flows, and we may or may not want those. And with that, it's time to wrap up. Thanks for your attention.